Good morning, everyone. I am very much thankful to our top leadership, Honorable Chancellor and Founder, Pro Chancellor, Vice Chancellor, Director HRDC, and Dean Faculty of Science to allow us to organize the Faculty Development Program on current trends in theoretical and experimental research in physics under the aegis of Human Resource Development Center, Integral University, Lucknow. Today is the fifth activity of the lecture series of Faculty Development Program. It is my honor to introduce the distinguished speaker and resource person, Professor Murali Manohar Verma, Department of Physics, University of Lucknow. Title of today's talk: A Search for the Model of the Universe, Lambda CDM or Modified Gravity. So currently, Professor Verma is a professor at Department of Physics, University of Lucknow. He is also Dean of Research, University of Lucknow. He has several positions around the world, like UNESCO Associate, the World Academy of Science, TAWAS, visiting scientist, CERN, Switzerland, visiting associate, Ayuka Pune, visiting professor and scientist, Cowley Institute of Physics and Mathematics, Japan, Institute of High Energy Physics, China, ICTP, Italy, Max Planck Institute for Astrophysics, Germany. He is also a coordinator of ICARD Center in University of Lucknow. He has more than 30 years of experience in academic and research. With this brief introduction, let me invite Professor Verma to deliver the FDP lecture.
Thank you very much. Thank you for inviting me. I I hope that my voice is going through well. If there are any hiccups or any problems, please do let me know. Um, I today actually I shall be speaking on this topic in cosmology, where we have a very important puzzle to be solved. And I would say that this is so important because we are trying to understand the nature of the working of our universe. And we have some information, but it is nowhere close to be accurate, so to say. So we have, as we do in science, the standard approach, the standard model to know about the mysteries, which is known as the Lambda CDM model. And then there are some alternatives also, which have been suggested of late. Because, doing research in science is an endless journey, and we never reach the final answers. So, this is the list of the things that I intend to cover. I may not be able to do that completely, but this is what I wish to talk about. The nature of gravity is so important that Newton, and even before Newton, many, um, say, intellectuals thought about how gravity functions, how things fall to the ground, and then what is the nature of that. So I will start with Newton, then go over to Einstein, because Einstein had his own version, the revolutionary version about the understanding of gravity, which is known as the general theory of relativity. And then this relativity theory applied to the universe, it gave a model which is known as the Einstein's model, although it turned out that it was not quite correct. And Einstein included one lambda term to make it correct. And that lambda is surfacing again. And this inclusion of lambda by Albert Einstein is also sometimes called to be blunder. It is said Einstein himself called it his blunder, included lambda, but now we are having the same lambda in other reincarnations. So, which is working well, and we have the model known as the Lambda CDM model, Lambda cold dark matter model. I will talk about that. So, there are challenges about this so-called standard model also, which are including the dark matter and dark energy, Hubble tension, sigma 8, and other kind of things. And therefore, being the endless journey, we shall go over to find out or discover some kind of other alternatives. They are largely known as the modified gravity. And then I will try to also present some of the technical details about this modified gravity theory, finally trying to see whether they are consistent with the observations or not. So, apple is, as you know, the most favorite fruit of the physicists. You know, the apple falling down, and then there is a feather, and they fall down with the same acceleration, which means that the acceleration is not a property of the objects, but it is related to something else. And that something else is the earth, you know, and that acceleration is the same for all the objects. This also gives us a reason to think in terms of a pseudo force, gravity as a pseudo force, and not as a real force. This is the idea behind a kind of equivalence, which also imposes us, or which behoves us to believe in some kind of equivalence between the inertial mass and the gravitational mass. Now, the idea about the gravitation was given in the mathematical form by Newton. And he showed that it is a kind of an inverse square law force, which is just like the electrostatic force between two charges. But it is always of an attractive nature. So that is why the things are drawn together. But Newton's law of gravitation, when applied to our solar system, could not explain a number of puzzles. I should uh, remind you that Newton's law of gravitation works very, very well, extremely well, when you launch the rockets, when you place the satellites into orbits, and in our, so to say, the daily applications or the usual applications of gravitation. That law is perfectly fine. But when we talk about the solar system, little about the Earth, we go to, let's say, uh, Mercury. Now, when you see the perihelion or precession of the perihelion of Mercury, I'll talk about that. Then there's bending of light, then gravitational redshift and gravitational waves. All these things are not explained in the Newton's law of gravitation. And then in 1915, as I just told you, that there came this general theory of relativity, which was the idea proposed by Einstein after a lot of hard work, hardship, and a lot of mathematical rigor also involved in that, which led him to announce to the world that gravitation is the curvature of space-time, and that curvature is caused due to mass or energy. So that was Einstein's view. The main puzzle about this precession of the perihelion, you can see that this is the orbit of a planet, so we shall call it Mercury for the time being. And this is the perihelion point here, this is the aphelion point here. And it was found that there is some kind of the precession of the perihelion, which means that the orbit keeps rotating. And this rotation was enumerated in 43 seconds, arc seconds per century. That was very small, but Newton's theory of gravitation could not explain it. And Einstein's general theory of relativity was a viable theory, and that would explain why the orbit of Mercury must precess. In fact, all the orbits should precess, but it is maximum for in case of Mercury. Then we had this bending of light kind of thing, which tells us that the path of light is affected by gravity. So when you have a star there in the background and you are sitting on the earth here and you find some kind of light coming from that star, it should have come this way, and when it passes, just grazes, as you can see here in a straight line, as it passes near the limb of the sun, it is slightly bent. That angle may not be very large. Numerically, that angle was confirmed through some eclipse in 1919 through the total solar eclipse. Uh, but then the important thing is to understand that the light from the background, as it passes near the sun, is bent and it comes to the earth. Thereby, when we observe from the earth, we extend this in this direction, and this is the apparent position of the star. So the actual position of the star was here, and the apparent position of the star is here, and this is the famous bending of light kind of thing that was verified through the total solar eclipse of 1919 by a team led by Arthur Stanley Eddington. This shot Einstein into fame, and that nearly confirmed the general theory of relativity. I must also tell you that in science, especially in physics, the theory is never confirmed and never final. It is only consistent with the observations. So we never reach the final frontiers. And that is the basic purport of our lecture also today, to bring home the point that we shall continue, in fact, um, striving for finding out the model of the universe, and we will never reach the final frontiers. Now, here was another effect which is known as the gravitational redshift, which means that as light is ejected or light comes out of a very heavy body, it loses its energy. And it is just like as if you throw something up from the surface of the earth, then the kinetic energy will go down. And similarly for the photon also, if you throw the photon through a laser gun up from the earth being in the high gravitational field, it goes into a lower gravitational field upward, and therefore will lose its energy. Now, losing energy is represented, as you will know, in terms of the frequency or the wavelength of the photon, and we say that the wavelength has increased. Therefore, in the high gravity regions, the wavelength is represented, these waves are represented by blue color, and here they are represented by red color, which means that the light is redshifted. And that is a purely gravitational effect. It is not arising due to any kind of Doppler uh, redshift, which arises when the source is moving away from the observer. There is no relative motion actually between these two objects. So, purely a gravitational effect. And that could not be explained in the Newton's theory of gravitation. But Einstein theory was, of course, very well good enough to explain it. So much so that we can apply it all to the massive objects like neutron stars, like black holes, and try to find out what might be happening. Now, the basis of the general theory of relativity came from the equivalence principle. And this general theory of relativity, as I told you initially, was later applied to the universe. That culminated into a form of the model called the Lambda CDM. So it is quite pertinent to understand this equivalence principle. What it says is that there are two spacecrafts. The spacecraft on the right is placed on the Earth, and due to gravity, as I just explained, that this light will actually bend, so it will start here. Suppose it's going from left to right, so it will start here, and by the time it reaches to the edge of the right, it will slightly bend down. Now, this effect is purely due to gravitation. Now, because of the equivalence, it will also happen almost in the same way. I'm saying almost with some caution, but it will happen almost in the same way for a spacecraft which is moving upward with an acceleration which is equal to g. Small g, as you know, is the acceleration due to Earth and known as the surface gravity of the Earth. And if this spacecraft on the left in the figure, if it is moving upward with a similar amount or same amount of magnitude of acceleration equal to g, then this observer will find a similar effect about the path of light. In fact, he will observe the similar effect for many other things also, like for other forces, right? Be it electromagnetic force or any other force in presence of gravity. So as the electromagnetic force behaved here in this spacecraft on the right, it will also behave the same in the spacecraft on the left. So primarily what it means is to say that gravitation could be uh, put equivalent to some kind of acceleration in the opposite direction. And this, according to Einstein, is expressed in the curvature. So in a nutshell, this is a classic picture which tells us another role for the apple. This time it is not Newton's apple, but it is Einstein's apple. And as you can see, that this apple is actually curving this space-time structure. It is you can also call it a cartoon-like thing. It is a cartoon where uh, apple has some mass, and because of that mass or energy, the space-time is curved. Now we say space-time here in a network, the curvatures are represented through a host of mathematical quantities. The theory is very, very elegant. The only thing is that you need a lot of this tensor calculus and tensor algebra to explain it. But it's so important because it tells us the um, basic ingredients or basic structure of space-time. So the matter curves space-time, and also the other way around. The space-time tells matter how to move. So once you have the space-time curve, then it will tell other things to move. So in a previous precession of perihelion picture, you can imagine that there is sun here and there is Mercury here, and then there is an interaction between Mercury and the sun, not through 1 by r square law, according to Newton, but through the curvature of space-time. Okay. So in general theory of relativity, we call it like this, that gravity is not a force, but it is a curvature of space-time. So once the space-time has curved, it will tell the planet Mercury as to how to move. And that is the reason for the precession, which was not explained by Newton's theory. Another observation that was made in 2015 was about the gravitational waves, which are completely absent in Newton's theory of gravitation, that cannot predict any gravitation waves. But Einstein's theory predicts the production of the gravitation waves, and they were already detected through some indirect means when people believed that gravitational waves carry away energy from some pulsars, and Hulse and Taylor had already got the Nobel Prize also for the discovery made much, much earlier in 1973. But this time in 2015, there was direct observation of the gravitational waves coming from the collision of two black holes. So these are the two big laboratories called the Advanced Laser Interferometer Gravitational Wave Observatory at two different places, Hanford and Livingston in the USA, where we have a Michelson kind of interferometers, and there are 4 kilometer arms here, and you can read a lot about them from internet. The result was that when you have two black holes actually like this, they in spiral, they come closer and closer. They move around the common center of mass, which is known as the barycenter. They move around, and a lot of, say, dynamics occurs with them. I'm not going into the details of black hole collisions. But then, as they are moving closer and closer, they are their quadrupole moment fluctuates, and gravitational waves are emanated. They are produced, and they come closer. By the time they reach each other and their event horizons actually cross, we call it merger, put up in B. And this is the merger point where the frequency increases, the amplitude also increases, right? And then crossing the event horizon, after that, there is a process or there is an event called the ring down. So they are completely, they stop and they become completely still. So these three phenomena are very, very important when you have the collisions between the black holes. And they were explained very well according to general theory of relativity. When the model was created, simulations were done, and there were people, in fact, C.V. Vishweshwara from India, who did a lot of work on the things called, technically called as the quasi-normal modes of the black holes, and they were actually found in this. So we had a good simulation, and a lot of effort was needed. Both of the detectors at two places did the same, and the important thing was that the profiles also matched to a great extent, so that we could call it a discovery. So here you can say that thanks and congratulations to that Lambda CDM model, we had the detections of the profiles taken at two places, which matched so nicely that it was kind of a confirmation of the another confirmation of the general theory of relativity. Now, there was also an observation, a point of observation, in fact, which are consistently going on right from 1933, when Zwicky had talked about the missing mass in the clusters, and it was found that there must be more mass than actually is seen. So more mass means there should be gravitational effects due to more mass. But then the light which is coming out, that tells us a different story, and that tells us that the mass is much less than what we gravitationally expect. So this is called in form of the virial velocities in clusters. There were a number of observations, gravitational lensing, CMBR. Now, gravitational lensing means you have a body which is bending, which is causing the bending of light. So by observing the bending of light, you can ascertain or calculate as to how much mass should be present. So it's called gravitational lensing, and that can determine the unseen mass. So I found that through some later observations by Planck and other spacecrafts, mainly by Planck, that around 26% of the total contents of the universe is unseen. It's called dark matter. 5% is something which is called the baryonic matter, which we can see, part of that. And remaining 69% called dark energy. Now, we do not know about these dark energy and dark matter components. As you can see here, Planck is the name of a spacecraft named after that famous illustrious scientist. So it was before Planck and it was after Planck. And you can see how the picture has slightly changed after Planck. The dark matter was 22.7%, it was expected to be. Now it is more. And ordinary matter has actually also increased. The role of dark energy has slightly subsided. So we can rely upon these numbers to some extent for the purpose of our understanding that this is the normal composition of the universe today. And the dark matter and dark energy, also known as the dark sector, which we do not quite understand even now, because we have to take them ad hoc. We have to include these ingredients. We do not still understand the nature of dark matter or dark energy. But both of them are included, and they must be included in maybe in an ad hoc manner, and known as the lambda CDM model. So what we can do about it now is one thing is accept the dark matter and dark energy and call it a lambda CDM model. This is one thing. or you can modify the theory itself. You can go a step say beyond Einstein's general theory of relativity and say that okay, that general theory of relativity was just a specialized case of some more general kind of general theory of relativity. Okay, so one could say that okay, we need to modify that gravity, and once we do some modifications in the geometrical part, in the geometry, then we will not need any dark matter or dark energy. So we had done some work through these papers, and where the geometrical effects were actually modified, and there was a procedure, cut and dried procedure for doing that. And when you do these kind of modifications, you suddenly discover that there are some new kind of fields which appear into your equations, which were not already present in Einstein's gravity. And those fields also undergo a chameleon mechanism. Each one of us must have seen the chameleon. And so there is some effect of the background on the mass of the scalar field. And then they need to be verified through the observations. But first thing first, so let's talk about the lambda CDM. Now the lambda, what is lambda? Lambda is some kind of a weird or very strange kind of matter which has negative pressure. So if you fill a balloon with lambda, then it will explode. Okay. And this was also the reason as to why Einstein brought this lambda term into his equations. When he applied the general theory of relativity to the universe, he found that okay, you have matter in the universe, and due to gravity, it should all close because gravity is the attractive force. So how to make it stable? In order to make it stable, Einstein at that point of time had included this lambda term in order to balance the gravity with anti-gravity. And thus he was able to obtain a static model of the universe. Just a few years later, it was found that around 10 years later, it was found in 1927 that the universe was not static, it was actually dynamical, it was expanding. And Einstein at that point of time, or maybe later, he is said to have called this inclusion of lambda as the blender. But now, in 1998 onwards, through some supernova experiments, observations, we found that the universe has entered a state of an acceleration, which means that it is not only expanding, which it was doing already so well. It is not only expanding, but it is actually accelerating. It is expanding in a very accelerated manner. And why should it expand in such a weird manner was beyond our understanding. So that ignorance was called as lambda. We call it in general a dynamical dark energy. And lambda is a special case of that dark energy with certain specific characteristics. But anyway, that lambda has the negative pressure, and that is able to explain the acceleration of the universe. Now, cold dark matter was already there because you need to have the cold dark matter in order to explain the observations, various observations, as I mentioned before, for the rotation of the galaxies, for the unaccounted matter in the universe, and, and of course, that was mapped through the lensing, gravitational lensing. So there was no doubt about it that if our theories are correct, then there should be more matter, much, much more matter than we had earlier expected, or we could see. And among the dark matter also, we could have hot dark matter particles, which are very light particles, but they also have a strong, a big kinetic energy, and therefore it's very difficult to hold them together and to cause the gravity that you require in order to form uh, the structures like galaxies. So hot dark matter being very light, having large amount of kinetic energy was good enough, not good enough, not at all good enough to have those structures. And therefore, it was conjectured that cold dark matter would play that role. Cold dark matter particles are heavier than the hot dark matter particles. They are cold in that sense that they don't have enough kinetic energy, and they are gravitationally good enough to hold these structures. So it so happens that you have a cold dark matter halo, a big halo, which creates the gravitation potential, and that attracts the normal matter of any kind. You know, for in those potential wells, and with those kind of collection or accretion, you can say, of normal matter, we begin the creation of the galactic structures. So first you have the cold dark matter halos, and then you have the baryonic matter collections or accretions towards the centers. And there are theories and models as to how this cold dark matter must be distributed throughout the entire space. Now it is dark because it doesn't interact with light. So electromagnetic light actually doesn't interact with this polar matter structures or the halos. The only way they can interact with the universe is through gravitation, which means that if you have two balls, two apples, one of the normal matter, another one of the cold dark matter, so you won't see the cold dark matter CDM apple. You would see, of course, the baryonic matter apple, but both will fall down towards the earth because the CDM has the that is influenced by the gravitation. Now, this kind of lambda CDM model, today we believe that it explains the universe quite accurately, because it explains as to how the universe must have begun, not exactly at the Big Bang. That is out of question because the lambda CDM or any kind of model that we have it based on the classical theories, that takes us only to the Planck era, Planck epochs, which were like when the universe was having the age of 10 to the minus 43 seconds. That happened when the energy scales of the universe were 10 to the 19 GeV. Before that, you need the quantum gravity, and the action itself becomes of the order of the Planck constant. So uh, the result in a nutshell is that this lambda CDM is good enough after the Planck epoch. It explains the things. Of course, there was an early process, uh, again a very strange process known as inflation that had to be included. Again, uh, you can call it artificially included into it because whenever we have to explain something, we inject or include some theories. That may not be always correct, but as long as it explains the observations, we can accept that kind of thing. So inflation is now an accepted theory, ingredient of the CDM. And then subsequently we had, after the radiation dominated era, uh, uh, there was an epoch which is called the recombination epoch, where the atoms uh, started being created. The first hydrogen atom. Before that, the energy level was so high that atoms could not be created, and radiation and matter, everything was collapsed in kind of a ball or something. So they coupled to each other. But then, when the atoms got created, then radiation was able to get free, and this is called the recombination epoch. And it turns out that it happened uh, around the time when the universe had the age of 3 lakh 80,000 years, roughly speaking. So we call it in terms of the redshift, when the redshift of the universe was, say, around 1000. So then the radiation got out from there because it got decoupled from the atoms. It no longer interacted with matter. And that is now called the cosmic microwave background radiation, CMB. So that is another success for the theories, which are this standard model, which is based on the general theory of relativity. Because we do the calculation based on that. and we need a theory actually of gravity which works for our observations. So that's why I say that it works, it explains the universe quite accurately. And we should also remember that it believes, or it founded on the Friedman Lemaitre uh, Robertson Walker metric, which is the homogeneous metric. And, it believes in the underlying assumption um, of the isotropy and homogeneity of the universe, which may not be quite true. And so there are problems with the Lambda CDM. So the first problem, as I just said, was due to dark matter and dark energy. They were brought in because we had some weird observations for the universe, and it seemed as if we had reached the state of checkmate, as happens in the game of chess. We had no options but to include the dark matter and dark energy, two unknown players, you know, and like you go to the crime site as a detective, and you are holding two persons as the culprits, for having created that kind of um, an incident. So call it dark matter and dark energy. And when you include it, lambda is refers to dark energy, a specific case of dark energy, and the CDM is of course this. So you have this lambda CDM model, as I told you, that works quite well. But it has the problems of several problems, like Hubble tension is one of the problems, and which means that the value of the Hubble parameter, which you obtain from the early universe, like from the cosmic microwave radiation, and when you try to calculate the values from the stellar dynamics or various stellar objects in today's time or later history of the universe, they do not quite match, and there is a discrepancy which is not acceptable. In fact, some discrepancies are always acceptable in physics because we know that we have the error bars. But if things go beyond the standard deviations, they are not acceptable. The same thing happens for S8, which is also enumerated in sigma 8 tension, which means again the fluctuations in the structure at the scale of around 8 megaparsec. And those correlations among the structures, when you calculate them over the spheres of 8 megaparsecs and you compare it with the observations, there is a kind of discrepancy which is again beyond the standard deviation and not acceptable. So these are among two main uh, difficulties or challenges, so to say, for lambda CDM. And one has to explain. I'm not saying that any other alternative is present or existing today which can explain uh, these perfectly well. But then it gives us some guideline as to what would be the possible solutions. Maybe we need to modify gravity in some way. So the dividends, the additional dividends of modification of gravity are that you don't need the dark matter or dark energy. Of course, the local gravity constraints, we have to verify the gravity, this modification of gravity with local gravity constraints and put up by the observations, and they are not yet consistent. We also don't know as to how the modification of gravity or any alternative theory of gravity would work throughout the history of the universe. Because in the standard format, we have a history of about 13.7 billion years, explaining various eras like radiation dominated era, followed by the matter dominated era, and then more recently the accelerated universe. So we need to have some kind of model that has the same robustness and same level of confidence to address these problems. Anyway, I will come to quickly modify it gravity kind of thing. And it is mathematical. More or less, I have a few slides which are mathematical. So I will just rush past those slides without, you need not worry about the mathematical details. The things I will tell you maybe good enough. So sufficient. So here is the action, as you know, for beginning a theory, you need an action. And it is like, you can say, the origin of the river, like Gangotri, from where the river will flow down. So action is like the Gangotri of the dynamics in any canonical theories. So we have this action which must be learned variant. And here we have generalized the Ricci scalar, which was Ricci scalar in the Einstein GR, but now it is FR. FR means a more general kind of a function of the Ricci scale. And this one is coming from the matter. So it is basically a relation between matter and geometry. Okay? In a nutshell, the theory is still fundamentally the same, that you have the matter that creates the geometry, curvature in the geometry, and then the geometry tells the matter as to how to move. We have only made some changes in the geometry. I must tell you that Lambda CDM people, in those models, there are changes made in the matter part of the action. So we do not include any artificial contents into the matter part in form of dark matter or dark energy. Rather, the geometry itself is modified with the hope that those kind of effects which are exclusively attributed to matter and dark matter and dark energy in the matter part, they would be transferred or they could be explained by this generalization of the Ricci scalar in form of the FR. So this is kind of an artifact that one should be careful enough while proposing the theories, and we should know our coordinates. We should know our intentions and hopes to what we have been doing. We also use this homogeneous isotropic, especially flat universe, the same thing. And then you get the field equations, just as the Einstein general theory of relativity has its own field equations. And you can always go from the Jordan, the so-called Jordan frame to the Einstein frame. You can look from that perspective also. I mean, you can change your glasses always and see what must have been happening in the Einstein frame. Then you realize, okay, there is some new scalar field that was not present before. So that scalar field gives you a new degree of freedom, and that degree of freedom can be worked out through this. As you see, this omega squared conformal transformation, it takes you to, it switches the frames, and the phi is the new scalar field. So you can see in this equation number 14, expression for phi. You know? So R was there, it was all Einstein's thing, but then you have now this phi thing also, which means that the scalar degree of freedom is there. Now, one more important thing about this new addition of the scalar field is that when you think about the gravitational waves, especially the polarization of the gravitational waves, in Einstein general theory of relativity, you find only the tensor modes of polarization. But now, if you modify and you include this scalar field also, you will have a scalar mode of polarization as well. And by future detections, if you are able to do those kind of detections, observations for, and if we observe the scalar modes of polarization, then that can be a verification, or that can extend the support to the modified gravity theories. Anyway, so I will not talk about this, how do we fix the form of FR and all that. I think this is not important for the purpose of my lecture, so I'll omit a few slides, even these ones, because scalar field has a mass, and mass is dependent on the parameters. And here we have shown how the mass of the scalar field The mass of the scalar field uh, would be somewhere tantamount to the mass of the conventional cold dark matter particles. So it's important for the purpose when we drive an analogy between the scalaron and conventional dark matter particles. So what I'm saying is that by tuning the parameters of the theory, you can always make the changes in the mass of the scalaron. And even in the lambda CDM, you have a huge scale of the mass of the dark matter particles, which is there. So what do we find then? The mass of the scalar field, which is the mass of the dark matter particles. And of course, the ground level fluctuation of that would be explained through the dark energy kind of effects when they will create the negative pressures in the universe. So actually, you are playing two different kind of roles. The scalaron is playing two different roles, one of dark matter and the other of dark energy. But they are not seen because the Compton wavelength becomes too small and the fifth force is almost screened. And we have to think about this kind of screening effect of the fifth force. And maybe why even the scalar modes of polarization, the gravitational waves, may not be actually observed because they can be screened out. But we have to see the local galactic scalar. There is some consistency with the local galactic and solar system constraints, but still the mm, things have to be settled with the cosmological observations. So I again will rush through them. And here I, I will explain to you what people have done over the years after the bullet cluster collision. It's a very famous cluster. It's a kind of collision between two galaxies. One is big, the other one is small. And they said that it extends a confirmation of the Lambda CDM model. Let's see why. This cluster is uh, present in Carina constellation, uh, long distance away from us. And what was found that it is a confirmation of the dark matter, which Lambda CDM includes. Why was it so? It was so because this structure overall collision was observed through the Chandra X-ray telescopes, and it told us how the X-rays could be produced. When the normal matter would agree to normal matter would come closer, so X-rays will be produced, and those X-ray images will be taken. So we know that these two red portions, they are close enough. The galaxies have actually crossed through each other, but the red portions are close enough. And the blue parts, which are basically the dark matter parts, in fact, they are the potential wells due to gravity. And as you know, I told you before that dark matter is like the halos, that creates the potential wells. Now, dark matter particles do not interact, or because of their very little interaction with each other and also with normal matter, except for the gravitational effect, they have been able to cross through. There's no electromagnetic interaction between dark matter loads, the dark matter halos. So these blue parts have easily crossed through without any interaction, whereas the red parts or the orangish parts, they basically are still not able to get through, and they are close enough because of the X-ray emissions. So here you can see in a better way, maybe these are the contours for the dark matter here and here, and the normal baryonic matter is still here. The dark matter has traveled a long distance, while the normal matter has not been able to travel that much distance. Okay, these two pictures have been taken, as I told you, with Chandra telescope, and this dark matter structures, they have been imaged through lensing. So, in fact, this was very, very important observation, and it was claimed that it puts aside all kind of the modified theories, because lambda CDM is good enough to explain that kind of interaction, zero interaction or very little interaction among the dark matter particles, and what it was saying, whole dark matter is there, the things are explained in the through the general theory of relativity, things are fine, and there is nothing to add. So it was hailed as the victory for the lambda CDM. However, in the modified gravity theory also, if you know the mass of the particles, if you can ascertain the interaction between those spherons, one could explain these things to a great extent, and that has been done. So the same thing in different colors. So these are the dark matter halos that have crossed through, and these are the dark matter which have not been able to cross through. So I have only referred to some kind of perspective with a scalar on mass that could be also invoked to explain these kind of pictures, and we can have the mass of 10 to the minus 3 electron volt that can explain it. And further investigations, of course, need to be made as to how these dark matter particles will interact. Now, almost at the end of my talk, I would show you this glorious picture, which is again a, a view, a simple view, in fact, at a glance for the entire universe. So here to the left, where you can see the bright spot with the slide, you may hypothetically it is kind of a big bang, which nobody understands today. And then, having passed some time, there was inflation. Inflation means that the scale of the length scales, they went up very, very fast due to some kind of the field, which is again lambda. So this lambda is playing an important role even here, causing the inflation to occur. The universe expanded exponentially. And then after around 4 lakh years, there was this afterglow pattern, which is known as the cosmic microwave background radiation, when the first atoms were formed, hydrogen atoms, electron and proton would come together because the nearby energy scales, the ambient scales, came down. But then we had the dark ages, and it was not before this time when it is called reionization that the universe lit up to the bright light, and we had the structures. As you can see, this edge on the top or at the bottom, this again starts rising here, which means that there is an accelerated expansion of the universe, and that is again attributed to um, the cosmological constant lambda. So this lambda is playing a role here. It is also playing the role at the inflation, and what Einstein considered his blunder is now turning into a boon, so to say. And we have these kind of spacecraft WMAP and Planck today. So the right side is today's observation, and we are able to observe the microwave background radiation. So finally, the summary is something like this, that we began our description about the Newton's theory of gravitation. We found that it has some things which it could not explain well, so it was replaced by a more accurate theory of Einstein's general theory of relativity. And when extended to the universe, initially it was a static model and it failed. I would say Einstein's model was a static model of the universe, and it was not correct. So Einstein called it blunder. But then later on, people included lambda and CDM. It worked. So now it is the standard approach for understanding the universe. But it has the ad hoc answers to some important problems. Only ad hoc means they are temporary answers. Nobody has been still able to detect the dark energy, detect dark matter. We only know the influences of these things, these entities, but there is no direct observation. And we don't have an answer to the Hubble tension, infinite tension in this. So there are a few challenges, in fact, despite all the glorious history of success of the Lambda CDM, we need to try the modified gravity in the spirit of science, I would say. Science always shows you the path, and as I emphasize again, that there are no final answers in science. Human mind is so small that it cannot capture all the complications and elegance of the universe. So one needs to explore the alternatives, and we have to think beyond the lambda CDM into the kind of alternatives available. Thank you very much for your rapt attention. I hope that it went, my sound, my voice went through well, and everything was fine. Thank you very much. I must thank the organizers again for inviting me, for making this presentation to you, and I would welcome your questions so much so that I can answer them. Thank you.
Thank you so much, sir, for this wonderful talk. So, audience have some questions. So,
Someone has written down a question. Please clarify where extra mass comes in a black hole when a star converts into a black hole. Now, uh, I hope my voice is audible well, right?
yes, sir.
You see, when a star converts into a black hole, there is no extra mass. There is no question of any extra mass. The star is there, it is contracting. Of course, it has to follow a limit which is known as the Oppenheimer-Volkoff limit. So it has to have a mass about 2 to 3 times the solar masses, you know. And if it is already qualified to become a black hole, it would continue shrinking to the size which is known as the Schwarzschild radius. When it has attained that size through the contraction, we will say that it has become a black hole and there would be no light coming out of it. Now, in this process of becoming a black hole and getting contracted to a size of the Schwarzschild radius, the star has not actually collected any additional mass. So there is no question of any extra mass in the black hole. The mass remains the same. That's it. Unless, of course, something else falls into it, it collides with something, right? As happens in black hole collisions, and then the event horizons they cross each other, then we can only say that the mass is increased. Otherwise, there is no question. For a single star, there is no question of any increase in the mass. That's it. You're welcome.
So, I have one question. So, in FR gravity models, some models have been ruled out by the gravitational waves due to
Which
extra
models?
degree of freedoms. In FR gravity models, I mean, in modified theories of gravity models,
Mm-hmm.
some models have been ruled out by the gravitational waves. There are a lot of reasons due to, I mean, degree of freedom. Uh, so, can you please make some comments on modified gravity models?
Actually, I would say that we can we do have the gravitational waves in the modified gravity models. The only difference is you said the degrees of freedom. Now the degrees of freedom is the epoch evolving concept, which enters through how the functional forms of FR are taken care of and what happens to the background effects which you take care of. The important thing is to know that there are some additional modes which would be created, imposed on the gravitation waves. Now, those additional modes of polarization will come through the scalar degree of freedom. And if they are detected, as I emphasized in my talk also, if you can detect some additional scalar modes of the gravitational waves polarization, then that would extend some kind of support to those kind of degrees of freedom. But other degrees of freedom may have their own set of polarization imposed on the gravitational waves. Now, if you compare it with the standard lambda CDM, you have only the tensor modes, which are plus and cross kind of polarizations. So there is no possibility of any additional degrees of freedom in the lambda CDM. Whereas in these kind of vast range of models, as you said, in we have a vast range of models, so scalar degrees of freedom would have their specific signatures which can be embossed on the gravitational waves, and that can be tested through the observations. Now, even if they are not observed, any any degrees of freedom, the signatures of them are not observed in the gravitational waves. It doesn't mean, however, that the modification of geometry does not work. It may be because of the suppression of those additional modes due to some kind of chameleon mechanisms. Okay, so there are papers and there are wonderful research work. You know, people are exerting, trying their way to say that there may be a suppression of the additional modes of polarization due to background. So there could be background related effects.
So thank you so much to find some time from your busy schedule and giving the talk here. So let me invite Professor Shaman Siddiqui, Head Department of Physics, Integral University, to address the vote of thanks.
Thank you so much.
Thank you, Dr. Shalam. So, first of all, I would like to extend my gratitude to the top leadership of the Integral University. That includes our Honorable Founder and Chancellor, our Honorable Pro Chancellor, Honorable Vice Chancellor. And then I'm also thankful to the Dean Faculty of Science and Director HRDC for helping us to organize such a wonderful events. And at last but not least, I would like to extend my gratitude to Professor M.M. Verma, sir. Uh, and as we remember that in last session, when we organized our refresher course, so he visited and he delivered a very interesting talk on gravitational waves, the wings of space-time. I still remember the title of the talk. And today, again, he presented a very wonderful, a very nice talk on the modified gravity and CDM model, and he covers all the aspects, all the theories of gravity from the time of Newton to Einstein and the modern, the present work. So I'm very much thankful to you, and because we were approaching the final semester exams, so that's why we scheduled this lecture online. Next time, sir, we will request you to again visit the university so that we
Yes,
can
yes,
get the
yes. Yeah,
maximum benefit from your knowledge. Thank you very much, sir.
it is always a pleasure for me to be in the company of the galaxy of all your stars of your department.
Thank you, sir. Thank you,
Uh,
sir.
Thank you, Shah
Thank you,
Alam,
sir, for
and
your kindness.
thank you, uh, Professor Shamun Ahmad Siddiqui
Thank
Sahab.
you.
Thank you very
Thank
much.
you, sir.
Hope to see you sometime again.
Okay, sir. See you.